Hello, everyone. We're going to go ahead and go over section 2.8, which is on one-to-one functions and their inverses. So we've learned a lot about functions at this point. We're now going to figure out what determines what a one-to-one function is. How do we find the inverse of one of those functions? So, all right, as an overview, inverse of a function that takes a given output and produces a corresponding input. So normally our functions work in the sense that we take inputs and we spit out outputs. But the way that inverse functions work is that they will take outputs and spit out inputs. So it's the opposite calculation of a function. The inverse essentially reverses or undoes whatever function originally did. So it's kind of like playing a reverse Uno card on a function. So that's what an inverse function does. It undoes everything that the function originally set out to do. So if the original function multiplies by 3, the inverse divides by 3. If the original function subtracts 2, the inverse function adds 2. Things like that. That's what you're going to see typically within inverse functions. Not all functions actually have inverses, but the ones that do we call one-to-one functions. So this idea of one-to-one functions is kind of how it sounds. It means that there is exactly one y value for every one x value. So no sharing values in this case, no two y values for every one x value or anything like that. So it's always going to be one x value to one y value, and that is it. So starting with one-to-one functions, our definition here, we say a function is called one-to-one if no two x values in the domain have the same y value in the range. That is, f of x sub 1 does not equal x sub 2, where f of x sub 1 doesn't equal x sub 2. So it's just this idea that every one x value has one very specific unique y value. There is no sharing of any values. So no two x values would be able to have the same y value. Like typically how we see with things like parabolas, where we see that like, oh, -2 and 2, the x values have the same y value for. Things like that. So a function that is one-to-one only, or a function is only one-to-one if it has no horizontal line that would intersect its graph more than once. So, well, we learned about the vertical line test and how the vertical line test determines if a equation is a function. The horizontal line test determines if a function is one-to-one. So we can use the horizontal line test now. So the horizontal line test works the same way you would use a horizontal line or anything that can act as a horizontal line. You would track your function up and down, and if your horizontal line passed 2 points, then it's not one-to-one because that means that two x values are sharing the same y value. So something like what we see in this graph over here, this does not pass, it is not one-to-one since we see this horizontal line going through the graph at 2 points. Another little kind of visual demonstration here is that if a function's one-to-one, once again, we see one x value for every one y value. So in this case, we're seeing every one value from this domain A has exactly one specific unique value in domain B. So we see that kind of like one-to-one tracking there. If a function is not one-to-one, it means that two values would have, one output value. So in this case, in domain A, 3 and 2 both share the same value of 4 within B. So that means that it's not one-to-one. There is no sharing values when it comes to one-to-one functions. So example 1, we want to determine if the following functions are one-to-one or not. We have A, f of x is equal to x squared. B, f of x is equal to x cubed, blanked on that word. C, f of x is equal to 3x plus 4. So we want to figure out if the following functions are one-to-one or not. The easiest way to do this is to graph the function, use a horizontal line test. You're not going to be asked very often if a function is actually one-to-one or not. And if you're asked to find the inverse of a function, you would just automatically assume that it's one-to-one. There isn't a whole lot of searching that needs to be done with this in the future, but we can go ahead and just make sure that we know our function is one-to-one. So we're going to go ahead, we're going to go to Desmos to graph these functions, and then use a horizontal line test to determine if it is one-to-one or not. All right, so here we are in Desmos. We're not going to use any notes for this problem just because we can answer with a yes or no very quickly. So we're going to go ahead and do our problems. We see here that on the side we have A, B, and C, and then we've added in a horizontal line here to use as our horizontal line for our horizontal line test. So, all right, starting with part A. Part A, there we go. We have f of x is equal to x squared. So we have this parabola. Let's just move our graph a little bit. Here we have, a good looking parabola here. But so we have f of x is equal to x squared. So if we bring in our horizontal line test, move it around a little bit. Oh, yep, no, it does not pass the horizontal line test. We see the horizontal line passes through 2 points here for basically every x value. We see that every y value essentially has 2 separate x values for pretty much every value there on our parabola. So this function definitely does not pass the horizontal line test since it crosses our graph many times in 2 spots. So problem A would be not 1-to-1. So let's go ahead and try out part B here. I'm gonna move our graph a little bit again. Part B, we have f of x is equal to x to the power of 3, so x cubed. If we use our horizontal line here again, we see, okay, it looks pretty good. Okay, we're a little suspicious about, x equals 0. So let's zoom in a lot. Zoom in a lot here. Zooming in quite a bit here towards 0. And if we use our line and we get up real close, I'm going too far. Here we go. Oh, it went by so fast because we're very zoomed in right now. But if we look at this, yes, it looks like it does get very close. And if you use something like Desmos, you will see that there are multiple x values that say it's equal to 0. But the thing with Desmos is that it doesn't have any small numbers that go past 5 decimal points. They don't include any numbers that have 6 decimal points. And the idea here is that Desmos says it's 0, but it's really not. It's really just some incredibly small number that Desmos has just said and rounded. It's 0. But when it comes to x to the power of 3, it actually is 1-to-1, even if our, graph isn't all that great, or, we're using Desmos where it rounds really small numbers to 0, and things like that. But x to the power of 3 is probably one of the more suspicious ones, just because it does have that kind of flat area there where the numbers are really small, but it really is 1-to-1. And it really just comes from the fact that when you solve for 1-to-1, if you wanted to do it algebraically, you would essentially be solving for x instead. And so really the only times you have a function that is not 1-to-1, it's going to be when you take an even root at any point that would give you that kind of plus or minus y value. So that's really the only time that you get a function that's not going to be 1-to-1. So even though Desmos, it's not perfect, it took those really small numbers and just rounded it to 0, this function really is 1-to-1, even if Desmos rounds. But so part B, f of x is equal to x to the power of 3, that function is 1-to-1. So, all right, our last one here. We have f of x is equal to 3x plus 4. It is just a straight line. It's going to go on forever in a straight line here. So we can use our slider. And yeah, it definitely doesn't look like it's going to cross 2 points really at any point here. So yes, our part C, f of x is equal to 3x plus 4 is 1-to-1 in that case. So, all right, that finishes up example 1. Let's go ahead and head on over back to the lecture. All right, we took a little peek at what 1-to-1 looks like on graphs and how to use that horizontal line test. So we finished up example 1. Moving forward here, we have the inverse of a function. So now we're really talking about the main point of our section here, inverses of functions. So we said before that establishing that a function is 1-to-1 will essentially just tell us that a function can have an inverse or not. If a function is 1-to-1, then it will have an inverse. And if it doesn't, then it won't have an inverse. And that's all we really needed to know what's 1-to-1 really mean anyway. So the main portion here is the inverse of the function. This is the one that we want to focus in on here. So The inverse of a function, we say let f be a one-to-one function with domain A and range B. Then its inverse function, which we say f inverse, that's that f to the power of -1 there. It doesn't actually have the power of -1. It's really just a notation that we use to indicate f inverse. So you will never actually be plugging in any powers of -1 or anything like that. It really just signifies f inverse. So that's why it looks like that. But so we have the inverse function f inverse has domain B and range A. See, we flipped those. So previously a function had domain A and range B. F inverse would have domain B and range A. So the same areas, they've just been flipped between domain and range. And it's going to be defined as F inverse of Y is equal to X, whereas f of x is equal to y. So remember how we said a little bit earlier, inverses will take in an output and spit out the input, where functions normally take in the input and spit out the output. So that's what we see here for f of x is equal to y. It's taking x, giving us y. Your inverse function takes y and gives us x. And this is for any y in B. So we also have a little bit of a visual here. These beans represent domains. So in A, in domain A here, we have x. Domain B, we have y, which is also equal to f of x. So our function will take x from domain A and give us y from domain B. But an inverse function will take y from domain B and give us x from range A. So we see it kind of flipped here, and we have our little text box here telling us this as well. The domain of f inverse is the same thing as the range of f, and the range of f inverse is equal to the domain of f. So we see domain and ranges are flipped for inverse functions, similarly as functions take in inputs to give us outputs, inverse functions take in outputs to give us inputs. So they're working in the opposite way. One is solving for x, the other is solving for y. So now we can talk about an inverse function property. So a property that inverse functions have is that they cancel themselves out with the normal function. So as an example, we say f is a one-to-one function. It has domain A and it has the range B. The inverse function, f inverse, would satisfy the following cancellation properties. So they're going to be able to cancel each other out. So they're almost the same. There's this one very slight difference. We say that if we take the inverse function of the original, that this would be equal to x. And we say that it's equal to x because this function is going to be equal to whatever's all the way on the inside of all the parentheses. If this said f inverse of f of 3, this would be equal to 3 instead of x. So it's just whatever is on the innermost parentheses, that's what that would be equal to. Because that f inverse and f are going to cancel each other out. But so the one main difference here is that if we take the inverse of the original function, our answer is x, but it's every x that's in the domain A, so the domain of the original function. If we do the opposite, we take the original function of the inverse of x, it's still equal to x, but now we're saying that it's for every value of x that's in B, range B. Range of the original, but we know that the domain is B for the inverse function. So the function that is on the inside, so the inner function is going to be the one that determines if x is in domain A or domain B, domain of the original or domain of the inverse. Domain of the inverse follows along with whichever is inside, whichever one is in the inside of those parentheses. So we saw that domain A went with f of x, domain B was f inverse. So it follows along in that sense. So conversely, any function f inverse that satisfies these equations would be the inverse. So if you had a function and you wanted to know if it was the inverse, you would go ahead, you would take the composition of that original function and see if it equals x. If it equals x, then yes, it's the inverse. These are composition functions if that was not clear when you looked at it. You're taking the composition of those functions and then they would cancel each other out. So for example 2, we're going to show that f of x is equal to x3 and g of x is equal to x to the power of 1/3 are inverses. So we're going to prove that 2 of functions are actually going to be inverses. So let's go ahead and go on over to our notes. All right, so with problem 2 here, we have f of x is equal to x to the power of 3 and g of x is equal to x to the power of 1/3. Now we have here on the side that property that we just looked at that said that a composition of a function and its inverse is going to be equal to x. The question that our problem poses here is, can we check that these two functions are inverses? So if we want to just check if they're inverses, we imagine that if we take their composition, the answer will be x if they're inverses, and if it's not x, then they're not inverses. So let's go ahead and take the composition of our two functions here. So we're going to do it both ways just to check and make sure that it is correct. But so let's go ahead. Let's start with f of g. So if we take f of g of x, which we know looks like this, we can go ahead and place them, compose them together. There we go. I guess that's a better way of saying that. So f of x is equal to x to the power of 3 is going to be in blue. G of x is equal to x to the power of 1/3 is going to be in red. So we want to start from the outside and work our way in. We know that f of x is equal to x to the power of 3. So we're taking our input, g of x, and we're replacing it with x. So within our function here, we're going to have g of x, which we know is going to be red, to the power of 3. We put some parentheses around that. But so we have g of x to the power of 3. Now we know what g of x is, so we can replace g of x as well. We know that g of x is equal to x to the power of 1/3. So we're going to have x to the power of 1/3, also to the power of 3. Now, if you remember exponent rules from some time way back when, we know that if we have a variable with a power and we raise that to another power, we get to multiply those exponents. So this is equal to x to the power of 1/3 times 3. 1/3 times 3 is 1, which x to the power of 1 is just x. So we have here that the composition of the two functions that we were checking was equal to x, which means yes, they are inverses. Okay, that was the highlighter, but you know what, it worked. All right, so yes, they are inverses. We took their composition, we got the answer of x. Now, if you wanted to try it the other way, it would still work as well. So if you wanted g of f instead, we would have g of f of x, where we knew that g of x was equal to x to the power of 1/3, which meant that we would raise f of x to the power of 1/3. And we know that f of x is equal to x to the power of 3. So we end up getting that x to the power of 3, also to the power of 1/3. Same exact problem here. We would get that x is equal to the power of 1, since 3 times 1/3 is 1, and the 1 doesn't matter. So once again, we see, yes, they're inverses. We checked both ways, and yes, we are sure. So these two functions, f of x and g of x, are inverses. So if you want to check to see if two functions are inverses, all you would need to do is take their composition. Wouldn't matter which way or which direction you took them, as long as you took the composition of those two, the answer should be x, or whatever's inside those innermost parentheses. Doesn't necessarily have to be x, but Even if you were asked what is, f inverse of f of 3, the answer is 3. The answer is always in whatever those innermost parentheses are going to be. I think you will encounter a question or two like that on your homework, so definitely be aware of that. If it gives you something ridiculous like what's f inverse of f of like 10.5278, it's that decimal number in the middle there. It would be that 10.728 or whatever I just said. But you get the idea. It's whatever's in those innermost parentheses, that's going to be the answer. The only thing that would slightly change would be if where it was found in the domain or in which domain, depending on which type of composition that you use. But I don't particularly remember any questions on your homework necessarily being like that. But all right, that finishes up example 2. Let's go ahead and head back over to our notes. All right, so that finished up example 2 there. So we can go ahead and move on to finding the inverse of a function. So we just looked at how to verify if two functions or inverses. Now we actually have how would we find an inverse given a function. So how do we find the inverse of a one-to-one function? If we're being asked to find the inverse, we can probably guarantee it's a one-to-one function anyway, so no need to double check or anything. So number 1, we would write y equals f of x. So since your function is going to be given to you in f of x is equal to some expression, you would just replace f of x with y. It just makes the rest of the problem a little bit more natural to use y instead of f of x, so you would change it to y just for simplicity's sake. Step 2, you would solve the equation for x in terms of y. So you would have y was equal to some expression with x. You would need to solve for x. So everything that's being done to x, you would reverse that, undo it, and do it to y. And that is if possible. If it's not possible, then you're pretty much done because that means that you just had y was equal to x. Then at step 3, interchange x and y. So once you have solved for x, you would just flip x and y again. That result is that y is actually equal to f inverse. So you would then replace y with f inverse of x, and there you have your inverse function. Let's go ahead and do some examples. Example 3, we want to find the inverses of the following equations. A, f of x is equal to 5x minus 3. B, g of x is equal to x cubed minus 1 divided by 2. And h of x is equal to 2x plus 1 divided by x minus 3. All right, so let's go ahead and do this problem in our notes. All right, so problem 3, starting with part A, we have f of x is equal to 5x minus 3. We are finding the inverse. So let's go ahead and write out our steps here. So step 1, we want to switch f of x out with y. So we're replacing f of x with y. So instead, we now have y is equal to 5x minus 3. Step 1 is done. That's it. Now we have step 2. We're going to solve our equation for x. So solving our equation for x means that we want to get rid of the 3, we want to get rid of the 5. Doesn't matter what we do to y, we want x by itself. So if we want x by itself, the first thing and easiest thing that we can do in this case is add 3 to both sides. So we would get y plus 3 was equal to 5x. Now remember, we're solving for x, we want x by itself. So we can divide each side here by 5. To represent what we did here. Now we're dividing by 5. So now we get that x is equal to y plus 3 divided by 5. There we go. We solve for x. So now, step 3 is that we're going to switch x and y back, then replace y with f inverse of x. So in this case, that means that we now get y is equal to x plus 3 over 5 which, replacing y with f inverse of x, we get f inverse of x is equal to x plus 3 divided by 5. And that would be our final answer. That would be our inverse function. So one thing that we can notice about our inverse function is that they're opposites of our original. Not necessarily, definitely not in the same order, but they are there. We saw in our original function, we subtracted 3 and we multiplied by 5. In our inverse function, we see we are adding 3 and dividing by 5. Once again, not in the same order, definitely not kind of exactly how we see before, but we do see those opposites occurring. We see that we're adding 3 and dividing by 5, whereas before in our other function, we subtracted 3 and multiplied by 5. So you're going to see that if you've done this problem correctly, you will kind of see those opposites happening. But once again, definitely most likely not in the same order, or even look all that similar, to be honest. But those opposites will be occurring. So, all right. Now on to part B. We have a little bit more difficult in this case, but not too bad. We have g of x is equal to x to the power of 3 minus 1 divided by 2. So, just like before, step 1 is that we're going to replace g of x with y. So we've got y is equal to x to the power of 3 minus 1 divided by 2. And there we go. Now step 2 is to solve for x. So if we want to solve for x, first thing that we can do is we really want to get rid of the fraction. We don't want to deal with the fraction anymore. So getting rid of the 2 would be the best case scenario for us in this problem. So we're going to multiply each side by 2. This will give us 2y is equal to x to the power of 3 minus 1. So, all right, great. Now we want to keep going. So the next thing that's going to be the easiest for us is to get rid of the 1. We're subtracting 1, so we're going to go ahead and add 1 to both sides. So this gives us 2y plus 1 is equal to x to the power of 3. All right, x is by itself, but it does have a power of 3 on it, which we really don't want. So in order to get rid of the exponent of 3, we need to take a third root. So we're going to go ahead and take a third root of both sides. When we take the third root of both sides, we get x is equal to the third root of 2y plus 1. And that finishes up step 2. Now our last step here, step 3, remember we're switching x and y, and then we're also going to replace y with f inverse of x. So first we're going to switch, so this becomes y is equal to the third root of 2x plus 1. And then we replace y with f inverse of x. So we get f inverse of x is equal to the third root of 2x plus 1. And this is our inverse function. Now, if you ever want to check if an inverse function is correct, you would take the composition of the inverse function and its original function to make sure that it was equal to x, which in all of our cases, they will. That's if you want to check to make sure your answer is right. But you can also do kind of a little bit of a half check. You're checking to make sure that all the opposite things are happening. We see in our original function, we're subtracting 1, we're dividing by 2, and so we're also taking a third power of x. So in our inverse, we know we should be seeing a plus 1, a multiply by 2, and the opposite of a power, which is a root. And it's always going to be by the same number. So if we had the power of 3, we're going to have a third root. So looking at our inverse, we have the third root of 2 times x plus 1, and those are all the opposites. So we can go ahead with like fair confidence that that's probably true. But if you want to be extra sure, take the composition. If it's equal to x, then they are definitely inverses. All right, let's go ahead and do part C. Now, if we look at part C, there's definitely something a little different here, and that there's an x in the numerator and an x in the denominator. And this makes this problem quite a bit more tricky. So let's go ahead and start. Step 1, we're replacing h of x with y. So we've got y is equal to 2x plus 1 divided by x minus 3. So we can go ahead and start step 2, which is that we're going to solve for x. So first thing, there's a fraction. Really don't want to deal with a fraction, so let's go ahead and get rid of it. Best way to get rid of the fraction will be to multiply each side by an x minus 3. So we're going to multiply each side by an x minus 3. This is going to give us x minus 3 times y is equal to 2x plus 1. All right, so quite a few things going on here. We've got x's in a few places. Let's just go ahead. Let's try to simplify a little bit. Let's go ahead. Let's distribute this y into our function of x minus 3. So in this case, we'll get xy minus 3y is equal to 2x plus 1. So, all right, this is our problem now. The idea is that we want to be isolating x because we're solving for x. That means that we need those terms that have x, we need them to combine. We need them to be one term. So what we're going to do right now is that we're going to take our x terms, meaning the terms that have an x in them, bring them to one side, and then we're going to take our non-x terms and bring them to the other side. So we'll have anything that has an x in it on one side and anything that doesn't have an x on it on the other. So we're going to write that off to the side here. So we're going to collect our x terms to, let's go ahead, let's bring it to the left-hand side. And I'm going to say left-hand side as LHS, so left-hand side. And our non-x terms to the right-hand side, RHS. So that's what we're going to do in this case. And let's go ahead, if we take a look at these, our x terms are in blue, x, y, and 2x. Our non-x terms are in green, negative 3y and plus 1. So we're going to go ahead. We want to collect our blue terms and collect our green terms. So let's start by bringing the x terms to the left-hand side. So we're going to bring 2x to the left-hand side. So we're going to subtract 2x from both sides. This will give us xy minus 2x. Let's go ahead and just put it right next to the x's. Minus 3y is equal to 1. All right, we've got both of our x terms on one side, but we still have non-x terms on both sides. So now we want to make sure to bring that 3y to the right-hand side. So we'll add 3y to both sides. Now we've got xy minus 2x is equal to 1 plus 3y. So now we see we have x terms on one side and non-x terms on the other. So this is what we wanted at this point. We wanted to have this. And we wanted this because of what's about to happen. We see that on the left-hand side, since they're both x terms, they each have an x in them. So if they both have an x, we can take that x out. We can factor the x out. So let's go ahead. We're going to bring this over here since we ran out of room a little bit. So we're going to factor the x. If we do that, it's kind of like pulling both x's out to the front. So we're going to get x times y minus 2. And this is equal to 1 plus 3y. So if we have x times y minus 2, and this is equal to 1 plus 3y, well, we want x by itself. The only thing left to get rid of is the y minus 2, which is kind of all by itself. It's just being multiplied by x, so there's no reason we can't just divide both sides by y minus 2. So now we get x is equal to 1 plus 3y divided by y minus 2. Now we see that x is isolated. It is by itself. We're going to highlight that in blue. We're not quite done, but we want to congratulate ourselves a little bit here. So we have that x is equal to 1 plus 3y divided by y minus 2. All right, now our last step, remember, switch x and y and replace y with f inverse of x. So step 3, we now have y is equal to 1 plus 3x divided by x minus 2. Now replace that y with an f inverse of x. An f inverse of x is equal to 1 plus 3x divided by x minus 2. And there we have it. So we definitely see a lot of opposites kind of going on here. This is our final answer. So this is our final answer. We're going to see some opposites going on. Since we did have a function where x was in the numerator and denominator, it did kind of change around our results just a little bit here. So maybe we don't exactly see the opposites occurring, but we do kind of see the same numbers popping up here. So it is a little bit different in that sense. When you do have a more complicated function, it may not be quite as clear with the whole, am I seeing the opposites? If you want to check, you can take the composition of the two functions, but let me just tell you, it's not going to be pretty, especially with functions that look like this. But all right, that would be how you would check to make sure this answer is correct. Let me just tell you, this answer is correct. This is the correct answer here for f inverse of x. So all right, let's go ahead and head back over to our notes or head back over to our lecture since we did just finish example 3. All right, so we just finished up example 3. So moving forward, we have our last concept here. We have graphing the inverse of a function. So we just went ahead and we learned how to verify two things are inverses of each other. We learned about one-to-one functions. We learned how to find the inverse of a function. So our last thing is graphing the inverse. So the graph of the inverse of f is obtained by reflecting the graph of f about the line y equals 0. So remember, reflecting was something we learned about in section 2.6. That's kind of that mirroring idea, but instead of mirroring across an axis, you would mirror across the line y equals x, which the line y equals x is just the line of slope 1 with the y-intercept being 0. So that's really what you have here. But honestly, there's an easier way to graph inverses of functions. So if we look at our images here, first, our image here on the right is just showing an example. So we have the line y equals x, we have our original function, and we see that it's mirrored. We see that if we were to take this and then fold it in half across that line, it would be the same image. So we have f inverse in red and f in blue. But if we look over here to the left, we actually have a little bit more of a helpful kind of hint here. If you were graphing the inverse of a function completely blind and you didn't know any point values or anything, then definitely going by what's on the right-hand side would be the most helpful. But as long as you have a few points, going by the left is actually much more helpful. Because really, what this is telling us is that if your original function has the value a comma b, meaning the x value is a and the y value is b, remember your inverse function takes the output and gives you an input. So really when it comes to the inverse function, x and y are always switched. So if you have the point, say a comma b in your original function, that means that that same point, that same area on your inverse is going to be b comma a, where the x value is b and the y value is a. So as long as you have a few points of your original function, you can flip the x and y values, replot those points, and draw in the same shape as your original function. So that's really all you would need to look for when graphing inverses of functions. You can flip the values of the points, graph those new ones, make sure it looks like the mirror image of your original. Let's go ahead and just practice that with our last example here. Example 4, we're just going to graph the inverse of the function using the graph of the function f of x is equal to the square root of x minus 2. That is also the graph that we have here for our reference. So what we're going to do is we're going to graph the inverse function. We're going to graph f inverse of x, given that we know that f of x is equal to the square root of x minus 2. And we have the graph right here. So we know that we're just going to make the mirror image of this graph across the line y equals x. So let's go ahead and do that in our notes. All right, so problem 4, we have f of x is equal to the square root of x minus 2. So in blue, we have our graph of f of x here. If we wanted to draw that line y equals x squared, we know that that line would probably look something like this. Just a slope of 1. Which is an example, that's most likely what it would look like. But when it comes to our graph here, we have quite a few points, and we're going to use those points. So we want to identify the best points that we have. This is the hand-drawn graph, so the points are a little more obvious than on the previous graph that you saw there. But so we're going to just figure out the values of these points. So this first one here is going to be 2, 0. Our second point here is 3, 1. This point right here is 6, 2. And I wrote that f of x right where I'm going to write that next point. But this last one here is 11, 3. So those are the values of our ordered pairs of f of x. Now, we're going to go ahead, we're going to do f inverse of x. So remember, we're going to take the same ordered pairs and just flip the x and y values. So for that first point, 2, 0, the point for f inverse of x will be 0, 2. So we're going to plot that point. We're going to label it. So you have 0, 2. Now our next point is 3, 1 on f of x. For f inverse of x, it will be 1, 3. So right about there. Then our next point, 6, 2, the point on f inverse is going to be 2, 6. So right about here. And our last point is 11, 3 for f of x. So for f inverse, it's going to be 3, 11. So it's going to be probably right about here. So we replotted all of those points knowing what the original points were for f of x. So now all we have to do is connect all those points and make it look roughly the same. So we're going to connect our points, do the best we can. And then we have it. It looks roughly the same. Looks like it could be mirrored across that line there. Remember this line was y is equal to x. Remember this is our function f inverse of x. So looks roughly correct. Once again, this is hand drawn. We're not looking for perfect. We're just looking for roughly correct. And that's what this looks like. But remember that key there was knowing a few points of the original function. Because if you know a few of those points, all you have to do is flip the x and y values, and that's the new point on your f inverse graph. So that's the key there for problem like number 4. So, all right, that finishes up our example. Let's go ahead and head back over to the lecture. All right, that was example 4, and that finishes up section 2.8. So in summary, in section 2.8, we covered what an inverse function is, one-to-one functions, inverse function property, finding an inverse function, and lastly, graphing an inverse function. So all about inverses, all about those reverse Uno cards. All right, that finishes up section 2.8, and I'll see you in the next one.